Hello everyone and be very welcome. My name is Guillermo and today we will be analyzing a real-life transport processes problem. First, let's read the problem and try to understand what we are dealing with, shall we? But first, remember to take pictures of every step that we take in order to solve the problem so you don't get lost along the process and you can check any information at any time. Now, let's go with the problem. Here we have the problem. So now I would ask you to take a quick picture of it so we could continue and I could explain you a little bit more about the process in a video we prepared for you. Here's the video. As we can see, an airflow is entering to the system through a compressor, and this is leading the flow directly into a first tank. Inside of this tank, there are little spheres of a material called zeolite. This is a really good adsorbent in the case of nitrogen. Now, as you can see, while the flow remains, only the oxygen part remains flowing, while the nitrogen part remains inside of the first tank. When this first tank becomes saturated, the flow passes directly to the second tank, which works basically the same. This gives time to the first tank to get free of the nitrogen, liberating it. And now, when the second tank remains saturated, it happens all the way around. It goes back to the first tank, and the second tank has to get free of that nitrogen. It's very simple, right? So, let's continue. The next step would be to determine the problem. And as you might have noticed, the main problematic in here is to calculate the time it will take to one sphere or bit to become saturated by the nitrogen in order for the feed to go to the second tank or back. But now there's a little trick in here because, as you might have noticed, the diffusivity equation that was given at the beginning included the term of temperature. And we don't have a temperature to work with, so what should we do? In this case, what we did in order to solve the first and the second part of the problem was to use a range of temperatures that goes from 174 Kelvin to 303. With this, we were able to calculate different diffusivities at different temperatures, and then calculate the time of each temperature. Now, let's go with the initial and boundary conditions. For the initial conditions, we would have that at time 0, there would be a concentration of nitrogen inside of the bit of 0. And for the boundary conditions, we would have that at an infinite time, the concentration would be 0.8, meaning that our bit would be saturated. And at some point, there would be a concentration of 0.75. Checking this one because it's a little bit lower than the 0.8 we have, which is the part we don't want to touch. Finally, our assumptions. In this case, it was assumed, first of all, this is a non-steady state problem. Then, diffusion occurs only in the z-axis. Then, diffusion remains constant all throughout the bits. And finally, there is no reaction. It is also important to mention that as bits are basically little spheres, we would be using spherical coordinates, and therefore we would need to use the unsteady state charts for spheres. Now, let's go with the resolution. Now, the first step in order to find out a resolution for this problem would be to determine the diffusivity of nitrogen in the bits using the equation given at the beginning of the problem. Our results can be seen in here in this table, where we can see a different diffusivity value for each temperature. This will be pretty useful for the last part of the exercise. And remember to take pictures so you don't have any doubts of how any calculations were made or how did we get any results. The next step would be to determine the values of x and x1 in our system, which in our case would be 0.5 for our x1, which is our radius, and 0.4, which is the point in which we will be interested for x. All this with the objective of finding out the relative position of the system, which leads us to the third step, which is finding the relative position, the relative resistance, and the unaccomplished concentration range. All this with the objective of finding the relative time of the system. Why do we need the relative time? Because with the relative time, we will be able to find the actual time it takes to generate all this process. Now that we have a relative time, the only thing we need to do is taking the original equation for relative time, clear out the term of t or time, as it can be seen in here. And next, the only thing we need to do is replace our values and find our results. Our final results can be seen in the following table. Finally, as a conclusion, we could say that this project was pretty helpful because even though it wouldn't be useful in a real-life process, because there are many variables we didn't take into account, it pretty helped us to find out how is that zeolite beads work, which is something pretty interesting and useful for the industry. And at the same time, this project was able to show us what is the relationship between the temperature of a system and its diffusivity, something that works in real-life oxygen concentrators nowadays. Also, it can be said that these kind of projects result pretty useful for areas such as filtration and purification, but still it can be said that this kind of process specifically isn't clear enough or with enough variables to be taken into account for a real-life process. So maybe adding some other tools or some other properties to the process, it might result in something that could be considered for a real-life process, or even though a real-life oxygen concentrator. Finally, we can say that our main difficulty was finding something suitable, taking into account the tools we had. But even though it wasn't easy, we think we made a good job, as we were able to find something that works in real life and that was actually useful to use in real life processes, not completely, but at least to generate enough information for us to understand what is going on, and finally get some results that would be helpful in some way, somehow in the future. Thank you everyone for listening. I hope you have a great day, and I hope to see you soon. Thank you.